Thank you. Thank you, Jeremy, and many thanks to Rahul, Uriel, and Kostya for this invitation. The talk that I'm going to present has been done in collaboration with Jason Picardo at IIT Bombay and with Emmanuel Plan, who was my former student 5 or 6 years ago, and who now has a position at the Vietnam National University. So the topic of this talk is how a polymer is deformed and stretched in a turbulent flow. So as far as the talk is concerned, a polymer will be regarded as a long elastic molecule, which can be which has an equilibrium extension and can be extended by a certain amount if the velocity gradient can do so. So this question exactly whether a turbulent flow can stretch and deform a polymer or not was asked first by Lumley in the 70s. Now it can seem an obvious question because we have studied Lagrangian turbulence, we have studied the deformation of line elements, the Lyapunov exponents, etc. But maybe at that time, it was not as obvious that in a flow where the strain is fluctuating, both in magnitude and in orientation, and in addition, there is a strong vorticity which can move a polymer away from the alignment with the straining directions of the flow. It was not obvious that in such a flow, a polymer could be deformed highly, compared, for instance, to a laminar extensional flow, where there is a persistent direction of stretching. So Lumley concluded that as a strong extension of the polymer, a strong stretching was possible if this product of the mean square strain rate of the flow and the correlation time of the strain is greater than the inverse of the relaxation time tau, at which the polymer relaxes back to its equilibrium configuration. Nowadays, we can read in this expression a kind of Lyapunov exponent, which should be larger than the inverse of the relaxation time of the polymer to equilibrium. After this prediction, we had to wait a certain number of years before this expectation was put into a systematic theory, which is due to Balkovsky, Fuchson, and Lebedev, and to Cherkov. Sorry, this is 2000, not 2001, the same year. Before I come to a summary of this theory, let me quickly introduce the ingredients. So the first one is how do we describe a polymer? One of the most common ways is as a chain of beads connected by springs. But as far as this theory is concerned, one can reduce to the case where only 2 beads are considered. And this is known as the dumbbell model, elastic dumbbell model. So basically one focuses on the lowest deformation mode of the molecule, on this, slowest oscillation mode of the molecule. And the 2 beads represent the ends of this molecule, while the spring models the entire elasticity of the system. In terms of the description, so the forces, the interactions between the polymer and the fluid are concentrated on the beads, so concentrated on the ends of the molecule. And there are 3 forces which act on the bead. A Stokes drag over a sphere with a coefficient zeta, then thermal noise due to the collisions of the molecules of the fluid with the polymer itself, and an elastic force, which is again something modeling the entropic forces in the molecule. And then there are some additional assumptions, some additional simplifications. The first one, to a first approximation, hydrodynamic interactions and excluded volume interactions between different segments of the polymer are neglected. The inertia of the polymer is also negligible. The Stokes number of the polymer can be estimated in a turbulent flow at something like 10 to the power minus 6. And since in most applications, the polymer is much smaller than the viscous scale, one can assume that velocity differences are linear over the size of the polymer. If one puts all these assumptions and simplifications together, one obtains this simple one-dimensional, ordinary differential equation, where R is the separation vector between the ends of the molecule, and where one can recognize these three forces. First, the stretching one, second, the relaxation, with a force that is nonlinear and diverges as the extension becomes comparable to capital L, which will then be the maximum extension of the polymer. These forces keeps the extension smaller than capital L. Greater extensions are not allowed. And then Brownian motion, this psi is simply white noise. As I mentioned before, this quantity tau represents the relaxation of the molecule once it is stretched back to equilibrium, and it can be multiplied by the Lyapunov exponent lambda of the random flow to form this dimensionless number, which is known as the Weissenberg number. So a small Weissenberg number means that the relaxation time of the polymer relative to the typical stretching time of the flow is small, and therefore stiff polymers, whereas for large Weissenberg numbers, this relaxation time is long, so polymers are highly deformable. The velocity gradient manages to stretch them a lot. Of course, this is an average quantity, and the local Weissenberg number can vary a lot, can fluctuate in a turbulent flow. Now, the other ingredients of the theory concern the flow. As you know, of course, the stretching, the ability of a flow to stretch a line element, and therefore a polymer, is related to the Lyapunov exponent. But if one wants to describe the full statistics of stretching, one has to consider also higher order moments of the Lyapunov exponent. High order moments of the size of a line element, and their exponential growth rate, which is known as the generalized Lyapunov exponent. When one looks at the generalized Lyapunov exponent as a function of the order of the moment, one obtains a function of Q, which has some very general properties which hold for any random flow. So this function has to be convex. It has to be trivially equal to 0 at the origin for Q equal to 0. The first derivative at the origin is equal to the Lyapunov exponent. And if the flow is incompressible, this function also vanishes at minus d, where d is the dimension, spatial dimension of the flow. In general, calculating this function analytically is a very difficult problem. There are very few examples where L of Q is known exactly, and one has to use numerical simulations. But even there, calculating these quantities is something difficult, especially for negative values of the moment, and also for very large positive values. There, as usually, high order moments of a quantity are difficult, require very large statistics, and converge slowly. Nevertheless, at least the core of this function or more precisely, its Legendre transform, the Cramer function, has been studied in several papers in 3D turbulence flows, and these are the main ones that are cited here. Now, with these tools, we can discuss the prediction that Balkovsky, Fuchson, and Lebedev and Cherkov made based on the large deviations theory. Here, I'm using the formalism that was presented by Boffetta, Celani, and Musacchio. They simply used, in the original version, the Cramer function is used, or the entropy rate function is used. Here, I'm using these generalized Lyapunov exponents, but as I said, there is only a Legendre transform between the two. So one main result is that the probability of the extension of the polymer has a power law shape between the equilibrium extension and the maximum extension allowed. Within this range, there is a power law behavior, which means that there is a broad distribution of extensions. And this independently on whether the flow is weak or strong, highly stretching, this broad distribution is always there. So there is coexistence of stretched and coiled polymers, though with different weights according to the strength of the flow. But in addition to making this prediction, this theory also provides us with a way to calculate this alpha in terms of the statistical properties of the flow or the velocity gradient, which are contained in these generalized Lyapunov exponents. Through this simple equation, one can calculate alpha from the Lyapunov exponents. And since, as we said earlier, this function has very general properties, we can deduce some properties of alpha of the exponent alpha as a function of the Weissenberg number for a general incompressible random flow. This is what I'm trying to do here. So when the Weissenberg number is a small, here I'm plotting the generalized Lyapunov exponent renormalized by the Lyapunov exponent. So at the origin, this convex function has a derivative equal to unity. So when the Weissenberg number is less than 1/2, the intersection between, so solving this equation means looking for the intersection between this straight line on the right-hand side and this convex function on the left-hand side. Such an intersection occurs at the positive alpha as the Weissenberg number is less than 1/2. When the Weissenberg number is increased, this straight line becomes flatter, the slope decreases, and therefore the intersection moves towards the origin. Alpha becomes smaller, and correspondingly, the power law tail raises until alpha becomes equal to, until the Weissenberg number is equal to 1/2. The straight line has exactly slope equal to 1, the same as the derivative of this function at the origin, and then therefore alpha is equal to 0, and the power law becomes equal to r to the power -1. When the Weissenberg number is increased further, the intersection between the solution of this equation moves to negative alphas, and this power law can even become -1 minus alpha can become positive, and so it can become an increasing power law, an increasing function of the extension. Then, of course, this holds for intermediate extensions. When the extension approaches the maximum length, there will be nonlinear effects which will stop the probability density function and make it vanish. Now, through this behavior, we see that in the limit when this L, this maximum extension, goes to infinity, the power law becomes non-normalizable, is no longer normalizable beyond a Weissenberg number equal to 1/2. Therefore, we can interpret this value 1/2 as a critical value, such that beyond this number, beyond this critical value, then polymers starts getting highly stretched. The amount of polymers who are highly stretched is considerable and predominant, and therefore one talks about a coil stretch transition in the configuration of the polymer. This name comes from an analogous phenomenon which is seen in laminar extensional flow at low Reynolds number. Now, I didn't mention earlier, but when the flow is when near to the origin, one can use a log normal approximation for the generalized Lyapunov exponent, which is a quadratic function. And so near to this coil stretch transition, one can even calculate alpha exactly in terms of the Weissenberg number. This approximation holds exactly for a Gaussian flow in one dimension and for a delta correlated flow, for a flow with the zero correlation time in general dimension. And this can provide, therefore, a first understanding of the dependence of this exponent on the Weissenberg number. Now, as I said, it is difficult to calculate this function, the generalized Lyapunov exponents, in experiments or in numerical simulations. But let me illustrate the use of this relation in a simple example where this can be done almost exactly, semi-analytically. This is the case of renewing a Côte flow, which is just a shear with an orientation which stays constant for a time equal to tau c, and then switches randomly after such a time. Every time tau c, there is a random rotation of the direction of shear. In this case, it was shown by Young that the Lyapunov exponent and the generalized Lyapunov exponent can be known explicitly. So in this case, there's no need to resort to the numerical simulation of the evolution of the dumbbell to calculate the generalized Lyapunov exponent. One can solve this equation directly by using this function. And one finds that an increasing deviation from the log normal distribution as the log normal prediction as the correlation function increases, but a very good agreement with this line in blue is the solution of the equation, and the dots are the results of numerical simulations. And so this somehow, if it was needed, it confirms the validity of the theory over a broad range of Weissenberg numbers. Let me also just make a small comment that this relation could be regarded as a way to use polymers to calculate the generalized Lyapunov exponents. This is because alpha is a monotonic function of the Weissenberg number. So the relation alpha versus Weissenberg can be inverted. And so Weissenberg can be expressed in terms of alpha. If one does so from the calculation of the alpha, one automatically obtains the generalized Lyapunov exponents. Of course, that there's nothing for free in physics. So this is just a limited satisfaction, because first of all, alpha only ranges between -d and infinity. So negative values of the negative Lyapunov exponents of the negative order are not accessible if the order is less than -d. And in addition, large values of alpha means small values of the Weissenberg number, and for small values of the Weissenberg number, polymers are very weakly stretched. So it is very difficult to detect a power law in the statistics and to calculate alpha and to measure alpha from the dynamics of polymers. Anyway, let me now come to how this predictions compare with the experiments and numerical simulations. So the first experiments were performed by Steinberg in his group at the Weizmann Institute. And I would perhaps say the only experiments are in a random flow have been done by Steinberg. And these happened much later compared to the prediction of Lumley. This is because, as you know, Lagrangian measurements became more routine much later, something like 20 years ago. And also to observe the dynamics of a polymer in detail, not only to track its position, but to track its deformation. That is very difficult in a fully turbulent flow because of the small size of polymers, which is below the viscous scale. So what made it possible to do so was the discovery by Steinberg itself of what is known now as elastic turbulence. So the addition of polymers in a viscoelastic fluid, to a Newtonian fluid, can generate a chaotic behavior even at very low Reynolds numbers. So can destabilize a laminar flow. So this can be used in a microfluidic device, which, because of its size naturally has a very small Reynolds number. So it can be used, this elastic turbulence can be used as a strategy to generate a random flow in a very small volume, where one can then observe the dynamics of a polymer. And one can record the extension and calculate its statistics. And these measurements confirmed the existence of a power law with an increasing, an exponent that increases a function of the Weissenberg number, and which was also related to the statistics of the stretching rates in this random flow, to the Cramer function or the generalized Lyapunov exponents. The same property, the existence of a power law behavior, was also observed in numerical simulations in very different configurations. This was done both by studying the statistics of a polymer along Lagrangian trajectories, or by evolving some continuum models derived from the dumbbell model and deriving the statistics of the extension from these continuum models. In both cases, one could find a power law behavior in a turbulent shear, in isotropic turbulence, in 2D, and in 3 dimensions, as well in a turbulent channel flow. And in addition, a similar behavior is seen not only in a passive simulation, where a single polymer is studied and the polymer doesn't affect the flow, but then also when there is two-way coupling, in particular by Rahul and Ruba, who are in the audience. So this somehow shows that there is nowadays a fairly good understanding of the statistics of a single polymer in a turbulent flow, and in particular a good characterization of this power law behavior and how it depends on the properties of the flow. And this understanding involves also a different, there is another point which I wanted to make before I summarize this introduction. As I said, especially in experiments, calculating this exponent alpha can be something difficult, because you know, one would need a large separation of scales between the equilibrium length of the polymer and the maximum length. So there recently another criterion has been proposed to characterize this transition from a coiled state to a stretched one. And this is to look at the entropy of the renormalized extension, where entropy is here meant in the sense of information theory. So we have seen that the distribution of extensions broadens. So the PDF becomes flatter and flatter as alpha increases before getting very steep at the large Weissenberg numbers. So there is a kind of, so the system goes through a maximum of spread of information around the transition from the coiled to the stretched state. So by borrowing an idea that was already discussed for extensional flows, Steinberg and Grisha, Lebedev, they recently proposed to characterize the coil stretch transition of, in random flows by looking at the maximum of entropy. Here, together with Stefano and Victor, we have also generalized this notion to different flows. I don't have time to go now through the details, especially because I've not discussed the laminar flows, but we have shown that this notion, the entropy of the extension, can be used to summarize into a scalar field several different properties of the coil stretch transition of polymers, and to compare how this differs in different flows, in flows with different properties. And we have also somehow pointed out that for random flows, it is more appropriate to look at the entropy of the logarithm of R, because this is the quantity which achieves maximum spread of information at the critical Weissenberg number. And this is because when one looks at the equations, if one consider in a random flow, the eddy diffusivity associated with this quantity rho would depend on rho itself, whereas when one moves to the logarithm, the eddy diffusivity depends on the Weissenberg number only. And therefore, if one looks at the transition as a function of the Weissenberg number, then it is this formulation which is more appropriate, because the noise whose amplitude increases with the Weissenberg number only depends on the Weissenberg number in this case. The Weissenberg number really becomes the control parameter of the transition when one uses this formulation. So now coming back to what I was saying, there is nowadays a good understanding of this transition and the dependence of the power law behavior on the different properties of the flow. And indeed, one can decorate the Dumbbell model and extend it, modify the flow to study various properties of this transition. One can obtain analytical results for a Gaussian isotropic delta-correlated flow, but one then can consider the correlation time of the flow as a parameter which can be varied, and study how the power law behavior of the statistics of the extension changes. One can introduce a dissipation mechanism in the internal dynamics of the molecule, which is due to different segments somehow entering into contact between them, and there can be friction, or friction dissipation due to in the bonds of the molecule itself. Then one can introduce a hydrodynamic or excluded volume interactions between the different portions of the molecule. One can assume that the polymer can break up beyond a critical extension. One can study the situation where the extension of the molecule can be even larger than the Kolmogorov scale, and so the polymer is exposed to a non-smooth velocity field. And one can introduce the effect of boundaries and study how the extension changes compared to, near to the wall, or compared to the case which I described so far, where the polymer is in the bulk of a turbulent flow. Now, I would like to add 2 more points to this list, and this is what I'm going to discuss in the remaining time. These 2 points are the following. Most of the intuition which I described so far is based on Gaussian models for the velocity gradient. So one question is how the non-Gaussianity of a velocity gradient affects this picture, if it affects it at all. The second point is, so far I've talked about the steady state, the statistically steady state dynamics, and the dependence of the stationary PDF of the extension on the Weissenberg number or other properties of the velocity gradient. But if I start from an initial distribution of polymers, how does it reach that asymptotic state? And this is an information which is useful for experiments, for instance, to estimate whether the measurements that are done are in the statistically steady state or not. Let me also, before moving to these questions, let me just clarify that I have completely ignored in this presentation what has been done in laminar flows, on the dynamics of polymers in laminar flows. But there is, of course, a huge and much larger literature on this problem, which also started much earlier. And in particular, there are certain properties like the coil stretch transition, which were first identified, which were first predicted in laminar flows, in extensional flows. And here are some review papers which describe this situation. So let me come to the first point. Why this question is it relevant? Why would one ask this question? The reason is that, so the non-Gaussianity of the velocity gradient. The reason is that there are now several studies which show that a non-Gaussian velocity gradient, that Gaussian models for the velocity gradient cannot be appropriate to describe the dynamics of particles in a turbulent flow. And these examples are, for instance, the following, these situations. If one looks at the orientation statistics of an isotropic particle, like a spheroid, it has now been shown that the alignment with the eigendirections of the velocity gradient cannot be captured by using a Gaussian model for the velocity gradient itself. The same happens, the sedimentation dynamics of non-spherical particles under gravitation in a turbulent flow was shown by Jean-Riddy not to be correctly described if one assumes a Gaussian statistics for the velocity field. And similarly, Jeremy has shown that the deviations of the statistics of velocity gradient from the Gaussian behavior has a strong impact on the formation of microscopic fibers, inextensible fibers in a turbulent flow. So it makes sense to ask the same question for the extension of polymers. So to do so, we have used 2 different sets of simulations. One is a Lagrangian simulation in isotropic turbulence, where we have kindly exploited a database of Lagrangian trajectories that Jean-Riddy has generously made available to us, not only in this occasion. And this is a simulation at a Taylor microscale Reynolds number of close to 100, with the Lyapunov exponent, which is in line with the previous observations in isotropic turbulence, and with two different correlation times for strain and rotation, again, with values which are compatible with the similar simulations done earlier at a similar resolution. And the database consists of a large number of trajectories. This fact allows us to obtain good statistics of the extension. And next to this, we have considered simulations for a Gaussian velocity gradient, simulations of the Dumbbell equation, where we have generated a velocity gradient which has a zero mean, and the strain and the vorticity tensor, strain rate and vorticity tensor, have an isotropic statistics, and two different correlation times, which are taken to be the same as in the direct numerical simulations. In addition, the amplitude of the two tensors, which needs to be the same in order to reproduce the relation between the energy dissipation rate and the square vorticity, which holds in isotropic turbulence. So this coefficient A is taken in a way as to have the same Lyapunov exponent as in the DNS. Therefore, this flow have similar Kubo number. So with this choice, we find these results. We can come to the results on the steady state PDF of the extension. So what we observe are minor differences, but systematic, and so something which can be explained. So on the one hand, it may be a good point that Gaussian model are close to the DNS. On the other hand, there is some physics in a turbulent flow which can be understood through this comparison. So what we observe is that at small extensions, at small Weissenberg numbers, the Gaussian flow stretches less than a turbulent flow. The PDF is steeper. This is simply because at low Weissenberg numbers, polymers are stiffer. And so the relaxation time is very short. Polymers immediately relax back to their equilibrium extension. Therefore, large deviations of the gradient from the mean are required to highly deform them, to see high deformations. And these bursts in the velocity gradient are much more frequent in a turbulent velocity gradient than in a Gaussian flow. Conversely, if we look at moderate to high Weissenberg numbers, then the relaxation time of the polymers is very long. And so the dynamics of the polymer has time to integrate the action of the velocity gradient over a long time. And therefore, mild stretching events, but more persistent, more frequent, which is what occurs in a Gaussian flow, are more effective in stretching the polymer that bursts that last for a short time. So at large Weissenberg numbers, we see that a Gaussian flow stretches more than in a turbulent flow. Then asymptotically, when the Weissenberg number becomes very large, the two behaviors become similar, become the same, because again, the dynamics then becomes integrated over very large times, and therefore the two behaviors, bursts followed by weak stretching or persistent mild stretching, becomes somehow equivalent. And also mathematically, the theory predicts that there is a single asymptotic value of alpha, which is equal to minus the dimension d, so -3, which is independent on the statistics of the velocity gradient. Now, to corroborate this understanding of the dynamics, we can also look at the notion of persistence, which tells us how much polymers remain the stretch state in the dynamics. This notion of persistence was applied to Lagrangian dynamics in turbulence in several occasions by, in the audience, Rahul, Dhruvo, and Somriddhi. And the applications were to tracers, to inertial particles, and to filaments in a turbulent flow. Here we have applied it to the polymer. And so one looks at the dynamics, a time series of the extension of the polymer, and identifies the time intervals where the extension remains greater than a given threshold. We have taken as a threshold half the maximum extension of the polymer, but we have also checked that the conclusions do not depend on the specific value of this extension, of this critical threshold, provided, of course, this is within the range of the extensions greater than the equilibrium one and smaller than the maximum one of the polymer. And what we found is that the statistics of these time intervals is exponential. And so we can extract a typical time, and we can show it as a function of the Weissenberg number. And indeed, we see that when the Weissenberg number is moderate to large in the Gaussian flow, the polymers persist in the extended state longer than in a turbulent flow. And this because, again, of what I said, because when the dynamics of the polymer is integrated over a long response time, a Gaussian, the mild but persistent but more frequent events that are found in a Gaussian flow are more effective in keeping the polymer stretched, rather than some bursts which die out very quickly. Let me now come to the second question that I wanted to address, is how does one reach the steady state? One starts from an initial distribution of polymers. How does one reach this power law behavior? And here we identify two different regimes. Now, the Weissenberg number, which distinguishes the two cases, is not 1/2, is not the one of the coil stretch transition, but it is 3/4. This can be understood, but incidentally, this value 3/4 is the value at which the slope of the PDF would be equal to 0. The PDF would be flat in the intermediate range. So first of all, for values smaller than 3/4, so weak to moderate stretching, we start with the we take the flow, we reach the stationary state, and then we introduce polymers with the initial PDF, which is the one which we would have in a still fluid. And then the black curve here is the steady state PDF with the power law predicted from the large deviations theory. And we observe that the steady state is reached by the power law, through a power law behavior. The PDF still has a power law shape, but with an exponent that evolves in time and attains the value, asymptotically attains the value which is predicted for the steady state statistics. This equilibration dynamics is exponential in time, and the dependence of this time scale t beta can be expressed, predicted semi-analytically. I'll come to this later. But for small to moderate Weissenberg number, the evolution is a power law that rapidly deforms and then raises up to the asymptotic value. Of course, this dynamic, the details of the evolution is depends on the initial condition, but the power law is seen also for different initial conditions. For example, if I had taken an initial condition with highly stretched polymers, I would have seen a rapid formation of a power law at steeper than the asymptotic one, which would have settled then to the asymptotic shape. And again, the dynamics would have been, the asymptotic dynamics is general and independent on the initial condition in the sense that it is exponential with this time scale. When we move to higher Weissenberg numbers, the behavior is very different. These two plots are for the same simulation, but the time at different, this is the initial stage, and this is the last part of the evolution. So initially, we do see the formation of a power law, but very quickly, a strong peak appears at at very large extensions, close to the maximum one. And when this peak forms, the power law behavior disappears, can no longer be detected, or the range where it was detectable shrinks, and the power law is no longer seen. Rather, this peak quickly attains its steady state shape, and then we see that the asymptotic power law, which is again in black, start emerging at large extensions and then to extend slowly to the entire regime. It penetrates the regime from the right-hand side towards smaller extensions. So a very different behavior. Now, this last behavior is, of course, difficult to predict because of the emergence of this peak, which therefore is an extremely nonlinear function. But the first regime can be deduced from the dynamics. Indeed, one can start by writing a advection diffusion or Fokker-Planck equation for the PDF here of the rescale of the extension rescaled by the equilibrium one. And this diffusion equation can be obtained in two ways. One, which is exact, if one assumes a Gaussian isotropic, statistical isotropic, and delta correlated velocity gradient, which is the Kragman flow in the Batchelor regime. Or more empirically, if one uses the same approach that he used by Richardson for particle separations, one can, in an isotropic flow, one can write down the equation for particle separation with also a restoring term due to the elasticity. And then one can assume that the stretching term, the action of the velocity gradient, can be modeled in an effective way by an eddy diffusivity, which, since we are in the viscous range, must be proportional to r squared instead of r to the power 4/3. So with this equation, then one can make an ansatz for this function, which is a power law r to the power square, r to the power 2 for extensions smaller than the equilibrium one, where thermal noise dominates. And therefore, this is just the usual statistics in Brownian motion. Then for intermediate extensions, we assume then as an ansatz the existence of a power law behavior with an exponent that depends on time. And then for extensions, this up to a given threshold length. And then beyond this length, we assume that nonlinear effects come into play, which make the PDF vanish rapidly. And therefore, we assume the existence of a functional dependence, which takes the statistics rapidly, the PDF rapidly to zero, and in any case, faster than this power law. In all cases, the normalization coefficient is left free and time dependent. So if we put this ansatz into the equations and make the assumption that there is a large separation of scale between the equilibrium extension and the maximum one, and we in this regard we ignore logarithmic corrections in the ratio between these two scales, we find that the deviations of the exponent beta from its asymptotic value solves these equations below and above the critical Weissenberg number up to the scale, up to the value 3/4. As I said, this analysis is only valid in the first regime. And therefore, we find that as a solution of this, that the existence of an evolving power law behavior is compatible with the equations as long as we are below the value of 3/4. And this exponent, the exponent behaves exponentially with a time scale that within these approximations where we have infinite separation of scales, that this exponent diverges near to the value 1/2 for the coil stretch transition. This is the behavior which is predicted. And of course, in a real system, this will correspond to a maximum of this behavior near to the coil stretch transition. This means that this power law behavior that evolves to the asymptotic state is the slowest near the coil stretch transition. And this is a further characterization of a phenomenon that we had called a critical slowing down near the transition, and that was characterized before in a different way by looking either at the eigenvalues of this Fokker-Planck operator as a function of the Weissenberg number, or by looking at the correlation time of the extension in numerical extension of the polymer in numerical simulations of isotropic turbulence by Côte and Watanabe. But anyway, this means that the dynamics, the equilibration dynamics in the flow is the slowest near the coil stretch transition. And this was attributed to the fact that this can be attributed to the fact that there is a wider distribution of polymers near the coil stretch transition, which is in line with what I mentioned before about the information entropy being maximum near the coil stretch transition. So with this, I will come to the conclusions. So the main messages for this study are the following. So if we replace the velocity, the turbulent velocity gradient with a Gaussian velocity gradient, we do see some deviations, which are not simply statistical errors, but have a physical, are the consequence of a different physics in the flow. But these deviations are relatively mild. Indeed, this can also be somehow expected because, as I said, I have related this power law behavior is related to the statistics of the generalized Lyapunov exponent. And the interesting range where we have to look in the generalized Lyapunov exponents is here at the negative values between -d and small positive values of the order of the exponent. And in this range, the function L of Q is quite constrained because it has to be convex and it has to vanish at -d and 0. So we cannot expect big deviations, very different behaviors of this function within this range. And this is, for example, exemplified in this statistics of the Cramer function, which once again is the Legendre transform of this of the generalized exponents in a turbulent flow from the data of Jeremy and his co-authors. We see that there are small variations from the log normal statistics. So this is perhaps a good point for models, for modeling of elastic polymers, because this Lagrangian simulation can be time consuming if one looks at fine statistics and one requires many trajectories, especially if rather than the simple dumbbell model, one wants to use more refined, more complicated models which better describe both the physics and the chemistry of a polymer molecule. The second point is that from small to moderate Weissenberg numbers, there is the steady state power law behavior is reached through an evolving behavior, which is itself described by a power law. So this is a critical point for experiments, because it tells us that the simple observation of a power law behavior cannot be taken as a confirmation that the statistically stationary state has been reached. And in particular, the time for the system to reach the statistical steady state in around the coil stretch transition, which is the most interesting situation, can be particularly long compared to the relaxation time of polymers. And so this puts a constraint on experimental observations and perhaps also numerical simulations. And the last comment I want to make is that these results that I presented were only for a dumbbell model, so just for the lowest relaxation mode of the polymer. But in this work, we have also considered a generalization to a 10-bead bead spring chain, and the results are qualitatively similar, provided a proper mapping between the parameters of the two systems is followed, of course, a mapping which was proposed by Lance Collins a while ago. And so a good qualitative agreement, very good agreement. And even quantitatively, we do not observe huge differences when the full deformation dynamics of a molecule is taken into account. And with this, I will conclude, and I'll thank you for your attention.
Okay, thank you, Dario. So we have time for some questions.
I think, let me ask you whether you are considering polymers actually dispersed in another fluid, or it's just a polymer flow, or polymer dispersed in another fluid?
Yes, no. In this study, I have considered a single polymer in a turbulent flow.
Okay.
I'm focusing on the individual dynamics of a polymer.
Okay.
This may hold if I also consider a very dilute solution. But the flow which I have considered is Newtonian.
Okay. Oh, you considered a Newtonian flow?
A Newtonian flow. Well, many of the simulations are done for a Newtonian flow, but many of these considerations are general. They would hold in any random environment, provided, yes, the flow is random.
Yeah, these some other questions are: did you consider surface tension effect? Surface tension between the polymer and the solvent or other fluid? Surface tension.
No. This is ignored in this description. It's one, as I mentioned, it is one of the variations that one could make on this dumbbell model to a first approximation by looking at the beads at the ends of the molecule only.
And I think you mentioned that the dumbbell model has been verified by using some type of a fluid structure interaction model, is it?
By using, sorry, what, can you take time by using which model?
The dumbbell model has been verified by some type of fluid structure interaction model done by some others. See, this problem, if you're considering a single polymer in a turbulent flow, then of course, dumbbell model is a very simple, quite a simple model, and then you can consider fluid structure interaction. It treats the interaction of the forces exerted by the surrounding fluid on the polymer and then predict the stretching or predict the deformation of the polymer in 3 dimensions, and then of course find out the effect on the flow field. That is fluid structure interaction problem, just as in a solid immersed in a fluid.
So for the case of polymers in a turbulent flow, this has been done at a still very simplified level, this taking into account the coupling of the polymers with the fluid, the two-way coupling, by assuming that the bead, still a dumbbell model, but with a bead which applies a force back onto the Navier-Stokes equation. And when one has an ensemble of these dumbbells, this can give a feedback which modifies the statistics of the flow. And this has been done, for instance, by Goto and Watanabe in Nagoya. But what you are saying, taking a complete fluid structure interaction description, it would be something very difficult for 2 reasons. One is that the polymers are usually smaller than the viscous scale. So one would need to have very high resolution for a turbulent flow to do that. And in addition, to get the statistics, one would need either extremely long simulations or many polymers. And so at this time, I think it's still very impractical.
Yeah, that is right. The time scales of relaxation and the turbulent time scales in the fluid, that may be, depends on the ratio of that. I don't know what is the ratio. It depends on the polymer. So that will decide the time required for a solution. I agree with that.
Yes. So maybe we can move to the next question. So there is a question by John online.
Hello, can you hear me?
Yes,
sure. Yes, thank you.
Yes. Dario, you talked about the grad U, the velocity gradient matrix.
Yeah.
Is there any evidence? Have you looked at what is the contribution between the diagonal elements and the off-diagonal elements in a polymer flow? And does it change with high and low Weissenberg number?
No, as far as I know, this question has not been addressed. What has been addressed is separately the action of the strain rate, so the symmetric part and the anti-symmetric part. Okay. But so typically, for instance, one has studied the PDF of the extension conditional on the QR diagram, QR plot. Yeah. But what you're saying has not been studied as far as I know.
Well, I'm just suggesting maybe it's worth looking at.
Is it this related to your work on quaternions? Is this?
Well, not necessarily. No, I think it's whenever you have flows like this with certain characteristics, it's always good to see how the contrast between a diagonal and off diagonal, which is the dominant part, if any.
Okay, thank you.
Okay.
No, I have a question. So Dario, basically, I guess that in order to reach polymer extensions which are of the order of their length, you need very long time scales.
Yeah.
Which are somehow somewhere in the inertial range of the turbulent flow. So I was wondering if you had any signature of this inertial range statistics, because we know that gradients along tracer trajectories could be correlated over very long times. So I was wondering if there is no evidence of that through some kind of Reynolds number dependence of the various.
No, yes. One point which I forgot to make is, of course, the Reynolds dependence of this study, in the sense that certain differences would probably increase with the Reynolds number, but still I don't expect much because of what I said. I don't expect the shape of this function to change dramatically within a reasonable range of Reynolds numbers. I didn't understand, though, your comment about the dynamics being controlled by the correlation times in the inertial range. Wouldn't it be rather
so for instance, if you measure correlation times component-wise of velocity, of Lagrangian velocity gradients, you observe things which are correlated over times of the order of the Kolmogorov time scale. But now, if you look at the amplitude, for instance, then you have long-range correlations.
Yes, yes,
which are behaving as a power law in the inertial range. And I was wondering if there is no signature of that in some, I mean, in one of the observables that you are considering.
Yes, I mean, but I mean, this answers only partially to your question, and I don't have it here. But if we look at that relaxation time to equilibrium, if it's here, I think, yes, here in this, sorry, in this figure, sorry, if you can see this figure D. No.
Yeah, we do see it.
This one, sorry, figure B. This is the delta correlated flow in black, and the Gaussian flow is the white, and blue is the DNS. There is perhaps an effect in the direction of what you are saying, of longer relaxations in the turbulent flow, but we didn't do more than this.
Okay, thank you. So I think we have to, no, we have to finish now because we are running out of time, and we have to have. So let's thank Dario again.
Thank you.